Okay, so in this video we're going to take a look at infinite series. And trying to find the sum by evaluating the partial sum when possible. Right. So an infinite series, again, we define to be just the sum of the terms of the whole sequence. Right. So in the previous section we talked about infinite sequences. And we talked about their convergence, which is different when we take a look at that same sequence and we add them up, right? We're going to use different techniques, right? The infinite sequence and those techniques are helpful here, right? But it is not as straightforward as the previous problem where we just took a limit of these a sub n's, right? So one of the ways we approach of solving these infinite series is by looking at what's called a partial sum. Right, so we define a partial sum, like the kth partial sum, has this notation, right, where we take a look at the sum n goes to 1 to k, right? So not an infinite one, right? So we look at a1, a2, all the way up to a sub k, right? So this is what we call the kth partial sum. Right, now, if the sum of a sub n is equal to s, right? So let's say s is a real number. Right, and we find that real number by taking the limit as k goes to infinity of s sub k. We define that to be s. Right, and if this converges to a real number, right, then the series converges. Right, so if s is a real number, or if the limit exists, then we say the series converges. Right, it diverges otherwise, right? Right, so either the limit doesn't exist or the limit is positive or negative infinity. Then we say that the series diverges. Right, so now let's take a look at an example here. Right, so the way we're going to evaluate these partial sums. Right, so we're going to look at the limit as n is equal to 1 to infinity of a sub n. We're going to take a look at the limit as k goes to infinity, n equals 1 to k of a sub k. All right, so we're going to take a look at this operation here. Right? Now, sometimes we do have the formula for the sum. Not always the case, right? In which case we use a different approach. But let's say for our example here, right, we have the sum n equals 1 to infinity of a sub n. Right, and I know that the formula for the kth partial sum, right, a1 plus a2 all the way to ak is given by 2k over 3k plus 5. Right? So let's say that I know that, right? I know the formula for the kth partial sum. Okay, so the idea here, and again here, what that would look like, right? So here, if I want to find the first partial sum, right, that would just be plugging in 1 for k. So that would be 2/8 or 1/4. Right, again, that's just plugging in 1 for k, right? And that's 2 would be 2 times 2 over 3 times 2 plus 5. So here we get 4 over 11, 4/11. Okay, all right, etc. Right, now here the idea here is that we create this sequence of partial sums, right, where this is 4, 1/4, 4/11, etc. Right, so this is different than the sequence of a sub n, right? This is a sequence containing a1, a2, a3, etc. right? Whereas the S sub k's for S1 is just simply A1, right? S2 is A1 plus A2, right? And A3 would be A1 plus A2 plus A3, etc., right? So let's distinguish between both of those quantities. Okay, so the idea here is that I can find the sum, right? I can evaluate this infinite sum, right? My infinite series by taking the limit as k goes to infinity of S sub k, right? So now it comes down to finding the limit of a sequence, right? And that I'm allowed to do that, or I can do that because I have a formula for the sum, right? So what this becomes is the limit as k goes to infinity of 2k over 3k plus 5, right? And again, here we see, right, we use techniques that we've learned for evaluating limits, right, where we have k's. They're both of the same power. So when that's the case here, where this k and this k is of the same power, that means what happens is that over the long run, right, as k gets larger and larger, right, these will converge to the coefficients of those powers, right? So this converges to 2/3, right? And more importantly, what we can say here is that now we've established that this is equal to 2/3, right? A finite value, which means that the series, in other words, the series converges, right? And it converges to 2/3. All right, now let's take a look here at a different series, right? Something called the harmonic series. Right, so the harmonic series is this series here, defined like this, right? 1 plus 1/2 plus 1/3 plus 1, plus 1/4, etc. Right, infinitely here. All right, now here, before we move forward and try to determine whether this is a convergent or a divergent series, I do want to point out, right, if we were looking at strictly the sequence, right, a sub n equal to 1 over n, right, now the limit as n goes to infinity of 1 over n is equal to 0. Okay, so let's just keep that in mind here, right? Now this is not the series, right? So here I bring that up because I do want to make a distinction between both of those, right? A common mistake here when we're working with a series is to treat them as a sequence, but that is not the case, right? The fact that the limit of the sequence is going to 0, right, does not actually tell me anything about the series. All right, that requires a bit more analysis, right? And in particular, this one, we're going to take a different approach than the previous example because I don't have a formula to calculate a sum. So instead, what I'm going to do is I'm going to focus here on a particular set of the partial sums. I'm going to focus on all the powers of 2. And by the powers of 2, I mean these, right? S8, right? 2 to the first, 2 squared, 2 cubed, 2 to the fourth, right, etc. 16, S32, and S64. All right, and the idea here is I'm going to bound them or show that it is actually unbounded and show that actually this series diverges, right? So if I think of, so S2, right, that would be 1 plus 1/2, right? That would be the sum of those first 2 partial sums. Okay, and S4 is going to be equal to 1 plus 1/2 plus 1/3 plus 1/4. All right, so the values themselves are getting smaller. All right, now here's what I'm going to do to show that I am unbounded here. So I'm going to have this kind of as my, I'm going to keep that block, and then the next 2 terms here, I'm going to say these are always going to be bigger, or it is bigger than 1 plus 1/2 plus 1/4 plus 1/4, right? So I essentially replaced 1/3 with 1/4, right? And again, 1/3 is a bigger value than 1/4, hence the inequality greater than. Okay, everything else remains the same except that 1/3 gets replaced by a smaller number. So this sum to the left is bigger. Right, now the reason I do that is 1/4 plus 1/4 is 1/2, so we get 1 plus 2/2. I'm going to leave it in this form to kind of establish a pattern of what's happening here. Right, so the next power of 2 is s sub 8, right? So again, that's 1 plus 1/2, right? And then I'll get plus 1/3 plus 1/4, same as before. And then we get plus 1/5 plus 1/6 plus 1/7 plus 1/8. And I'm going to do the same thing I did above, right? Where I'm going to replace here. So I'm going to almost group these here, right? 1 plus 1/2 plus 1/4 plus 1/4 for, as previously, right? The 1/3 and 1/4. And then for the next group of 4 terms, right, I have 1/8, and I'm going to replace the previous terms with 1/8. And again, right, 1/8 is the smallest of these values, hence this inequality still holds, right? So we'll get 1/8 plus 1/8 plus 1/8 plus 1/8, right? And more importantly, each one of these is a half, right? So now what we have here, this quantity is, right, greater 1 plus 3/2. Okay. All right. And now we can start to see that what's happening here when I kind of check in at each one of these powers of 2, right? Because I'll do the same thing for 16, where we're going to have this same for 8, and then the next 8 terms, I can make an inequality where it's bigger to 16ths and I get another half, right? So what's happening here is that I can bound here or provide this inequality where I can do the same thing where I can, at each step of the way, I'm adding another half, right? Excuse me, that's 4/2. When I check in at S32 using the same process, right, I add 5/2, right? And then the same thing for 64, right? This is going to be bigger than 1 plus 6/2. Right, so what I'm doing here, I'm establishing that this sum is getting bigger. Right, I'm actually saying that at each step of the way, that I can establish this inequality. Right, I'm going to have 1, and then by however the power here, right, that's 2 to the 4th here. Right, so it'll be bigger than right, n over 2, right? That's how many halves I'm adding, right? Now, here it might look a little odd because I'm not looking at any of the other powers in between, but, you know, that's okay because here I'm establishing that what's going on here is that the sums are getting larger and larger, right, as I check in, right? As I check in these powers of 2, right? So here, what I've established, if I let n go to infinity, then s sub 2n is going to be greater than infinity. So what that tells me is that it is actually unbounded, right? If some value is bigger than infinity, what's just telling me it's an even larger value than infinity, right? More importantly, right, the limit as n goes to infinity of s of 2 to the n, right, is infinity. In other words, it's unbounded, not a real number. So what this tells me is that the sum 1 over n is divergent. All right, because that sum is getting larger and larger and larger. Right, so it's not the converging, the partial sum is not converging. Right, and again, I do want to bring your attention here to the first part where we saw the sequence does converge, right? Each individual term does tend to 0, but the accumulation of these terms, adding them, does not actually converge to a particular sum. It is a divergent sum. Okay,